So we're going to learn the basics of something called stoichiometry today. Stoichiometry is a pretty big word, but what does it mean? It's really not that hard once you understand what it means. So stoichiometry is just a way to show the relationship between mass or the amounts of reactants in products. So when we talk about stoichiometry, we're talking about showing relationships between products and reactants. And stoichiometry will tie everything that we've done so far this year together. So think back all the way to Unit 1 when you learned how to factor label. We're going to use factor labeling here. We're going to use Unit 2. We learned how to name compounds and write formulas. We're going to use that information. Unit 3, we learned how to do balanced equations and predict products. We're going to use all of that stuff. So something from every single unit is going to be tied up into stoichiometry. So it says it shows the mass or the amounts between relationships between products and reactants. Now here's the key thing. This cannot be done unless you have a balanced equation, because balanced equations show the reactants and the products. So we have to have a balanced equation. It's so important. You must have this balanced equation. Otherwise, we're not showing relationships between reactants and products. So that's very important. So let's talk about a balanced equation. You already know how to balance equations, predict products, and then balance the equation. You've got all of that. So some information that we can get from a balanced equation. One thing we are able to get is the relative amounts of moles. So the number of moles of the substances involved in the reaction, whether it's products or reactants. So your coefficients can show you the number of moles. So the coefficients in front of the reactant or the product, that tells you the number of moles of substance, how many moles that substance is involved. And also, those coefficients can tell you the number of particles. So the same coefficients can tell you the moles, but the coefficients can also tell you the particles. So thinking back, we talked about particles in terms of Avogadro's number. Particles can be molecules, atoms, formula units. Remember, just a quick refresher, molecules are for covalent compounds and for diatomic elements. And formula units, these are for ionic compounds. So if we talk about an ionic compound, its type of particle is a formula unit. And then the last thing, when we balance an equation, we abide by the law of conservation of mass. So every balanced equation abides by the law of conservation of mass, which says the number of grams that you start with have to equal the number of grams that you end with. So the mass of the reactants will always equal the mass of the product. So that's very important. When we get into something called limiting and excess reactants, we'll really be focusing on making sure that the grams of the reactants are equivalent to the grams of the products. So we're going to start off with an example. Our first example is going to be very basic. It's just called a mole to mole conversion. So in other words, we're going to start with moles and we're going to end with moles. So the question says, how many moles of ammonia are produced when 0.600 moles of nitrogen reacts with hydrogen? So we said we always have to start with a balanced equation. So it says nitrogen is reacting with hydrogen. We must remember that nitrogen and hydrogen are both diatomic elements. If we forget to make them diatomic, then it's going to mess up our whole equation. So this is just a basic synthesis reaction. Nitrogen plus hydrogen makes NH3. You don't need to worry about states of matter because they're not going to affect our stoichiometry. You can always stick them in if you know what they are, but it's not necessary. Now this is not balanced because I have 2 nitrogens in the reactants and only 1 in the product. So I'm going to stick a coefficient of 2 in front of the ammonia. Now if I do that, I have 6 hydrogens as a product. So let's put a 3 in front of the H2. And now we've got 6 moles of hydrogen on each side. So it's all balanced. So one thing I like to do after I write my balanced equation is write the information that I know from the actual question underneath my equation. So I'm going back. It says how many moles of ammonia. So I'm looking for moles of NH3 so that now I can not have to read the problem again to figure out what I'm looking for. And it says how many moles are produced when 0.600 moles of nitrogen. So we have 0.600 moles of nitrogen reacting with H2. So we're just going to do some factor labeling. So the information we have is we have 0.600 moles, and it's going to be really important that you write of N2 because look at what we're looking for. On the right side over here of my factor labeling, I'm going to write moles of NH3. So we need to get moles of N2 to moles of NH3. Now, When you do stoichiometry, there is not a 1 written in front of the N2, but that's understood that there's really a 1 here, right? Even though we don't write it. So we can get mole ratios from the balanced equation. But it has to be balanced, okay? So you have to make sure your equation is balanced. If it's not balanced, then the mole ratio doesn't work. And this is by using coefficients. So that's why we have to make sure it's balanced. So what you are able to do is you can pull any two things out of the equation that you want. So I could, if I want to look at N2 and H2, I could say there's 1 mole of N2 in this reaction for every 3 moles of H2. Now, these mole ratios are specific to this reaction right here, this synthesis reaction. And of course, you can always flip conversion factors over. So I could say 3 moles of H2 to 1 mole N2. But you could also pull something from the reactants and from the products. So maybe I don't want to compare N2 and H2. Maybe I want to compare N2 and NH3. So another conversion factor I could have is 1 mole of N2 for every 2 moles NH3. And of course, it's a conversion factor, so you can flip it. 2 moles of NH3 to every 1 mole N2. And finally, if you wanted to, you can compare the H2 to the NH3. So we could have 3 moles H2 to 2 moles NH3. And of course, 2 moles NH3 could be on the top and 3 moles of H2. So you can pick any two things, any two substances, particle types, out of the balanced equation and compare them. Okay, so if we go back to our problem, we know that we need to have N2 in the denominator, and I want moles of N2 because I have to get that to cancel out. Now I need NH3. Well, my balanced equation has N2 and NH3, so I can say moles of NH3. So those coefficients can be moles. And this is called a mole ratio. But this mole ratio, we've used mole ratios from um, formulas before, but this mole ratio is from the balanced equation. Okay, so what I'm going to say is look at the coefficients. So again, use the coefficients. That's key. So if I look in front of my NH3, I have a 2. So I'm going to have 2 moles of NH3 and 1, even though I didn't write it. I usually don't write the 1. I know it's 1 there. All right, so my moles of N2 are going to cancel out. So my moles of N2 cancel out. I'm left with moles of NH3, which is what I wanted. So I'm going to plug this into my calculator and get my answer. Now, if we think about significant figures, because we've got to remember that this has 3 significant figures. The zeros here are at the end of the number and to the right of the decimal. And this is infinite significant figures. It's a conversion factor. So the 2 to 1, it's exactly 2 moles of NH3 for every 1 mole of N2. So our final answer, we should have 3 significant figures. So I do the multiplication and I have 1.20 as my answer. So I get 1.20 and I'm done. So you've done your first stoichiometry problem. Now let's do something that's a little more complex. So this was starting with moles, ending with moles. Now we're going to start with mass and end with mass. So it says calculate the number of grams of ammonia produced by the reaction of 5.4 grams of hydrogen with nitrogen. So it's our exact same balanced equation that we had in the first example. So we're just doing different numbers here. So we still have a synthesis reaction. 1N2, 3 H2s yields 2 NH3. So let's start by pulling out all the information from the problem. So calculate the number of grams of ammonia. So I'm looking for grams of ammonia. And this time I'm starting with 5.4 grams of hydrogen. Okay, so now I don't have to read the problem anymore. I know everything that's given in the problem. So I'm going to start with 5.4 grams of H2, and ultimately I'm going to try to get 2 grams of NH3. So let's think back to prior units. How do you get rid of grams? Well, whenever you have grams, the way to get rid of grams is to use molar mass. So we'll look at the periodic table. 1 mole of H2 is 2.02 grams of H2. So by doing that, I've eliminated my grams. So my grams of H2 are gone. Now I have moles of H2. Now remember, I'm trying to get to NH3, so I look at my balance equation. There's 2 moles of NH3 for every 3 moles of H2. So I need the H2 in the denominator, so 3 moles H2 to 2 moles NH3. What that does now is eliminates my moles of H2. So now what I've done is converted H2 into NH3. So my H2 is gone. Now, right now, I'm left with NH3. So we have moles of NH3, but we need grams. So again, we can use molar mass. Whoops, we want moles on the bottom. So 1 mole NH3 in the molar mass is 17.03 grams for NH3. So that has now just canceled out our moles of NH3, and we are left with grams, and that's what we need. Now, a few quick things. Let's make some notes under all of this stuff. This we used here, molar mass. Just right from your periodic table, right? We learned how to use molar mass earlier, so that's from your periodic table in our prior unit. Here, this is called a mole ratio, and this is from your balanced equation. And then again, we had to get back to grams, so we used molar mass again from the periodic table. All right, and now we just plug all of this into our calculator, and we have to think about significant figures. So 3 significant figures. Molar masses are not exact, so we'll say that's 3 significant figures. Infinite, because we're getting mole ratio, and then here we'll count it as 4 significant figures. So our least amount is 3. So our final answer, when we plug this into our calculator, we should end up with 3 significant figures. And what I got, and you should practice calculating it, is 30.4 grams. So here is my answer, and that 30.4 grams, this has 3 significant figures in it. So sometimes you have to go from grams to grams, sometimes moles to moles, sometimes moles to grams or grams to moles, just depending on what information is given. But in stoichiometry, you always have to start with a balanced equation. So now we're going to take some time to practice this to make sure that you've got it. And once you practice it, it becomes super easy.